Welcome to the next video. Today we're going to look at Toluene disorder. So here we have raw data, and I always recommend before doing any structure solution or refinement, just have a look at the raw data, the frames, and how many of the reflections actually index. So you can see that, well, on this frame it doesn't look that bad, but in some of the frames you can see that the reflections are kind of split, right? So it's not as single crystal as you would like. If you have a look here, we can see that, well, actually it's not that bad. Almost 94% of the reflections indexed. That's already after I did peak hunting before and found cell. So the cell is triclinic. We can have a look at the eval sphere. We can see that we have 37,000 of indexed reflections and about 2,500 reflections that are not indexed. Okay, so we see that there were some issues, but there are a lot of reflections that indexed, and in fact this data set is fine even if you just treat it as a normal single crystal. Treating it as a twin doesn't really give better results, so let's just treat it as a single crystal. So I processed it, and now let's have a look at the structure solution. So that's how structure solution looks like. So we can see we have two ions that are barf anions. So we have these four aryl groups with four pentafluorophenyl groups connected to boron. Here we have sulfur, it's a thionthrenium salt. And here we have another thionthrenium cation. And here is something that looks like a toluene. So to make it a bit cleaner, I can delete that, delete that, delete that. Here, place carbon atom. And from the crystal structure, that's a symmetric unit, we can say that it's a monoanion of thionthrenium. It's a thionthrenium cation because we have two cations and two anions in the crystal structure. But okay, let's see how it looks like. Let's do some refinement. I'll just change to Shelix. Okay, and maybe 4 cycles. Let's refine. Okay, it doesn't look bad, right? I can do now anis to switch to anisotropic refinement from isotropic, Control R to refine again. And well, it actually looks pretty good, right? We can already see some hydrogen atoms on the thionthrenium cations. But here something weird is happening. Okay, so there's some disorder, probably. So how do we handle that? So at first, it's always a good idea to switch to isotropic refinement in the disordered part. So I'm going to now press Shift and just drag over the toluene molecule. And I can type, for example, type isot. And now only this part that I highlighted is isotropic. Or I can just click here. So Control R again to refine. You can see that some additional peaks are now probably more visible. So something we can also do is to lower occupancy. Because if there is a second disorder component, if you lower this one, the second one might get more visible. Yeah, so to me, it looks like we have one toluene, which is the one that we have in the model right now, but there is also another toluene molecule with 6 carbon atoms here and the metal group right here. So we're going to take care of that right now. So I'll just go back to initial occupancy for now. Okay, so before dealing with any disorder, I always recommend to renumber atoms. So I'm going to call this one name C1, name C2, name C3. If you have a lot of atoms, you can also go to naming. You can start with 4, type C. So that was number 3. Here will be number 4, 5, 6, 7. Escape, and now they're named. Okay, let's just click refine again. Okay, So we're going to try to do it in 3 different ways. In this video, I will show you 2 ways of doing that stuff, and later I'll show you another methods. So at first, let's actually discuss what we are going to do. So we want to split these 7 carbon atoms into 2 disordered components. That one will be part 1, and the second orientation of toluene with benzene ring here and methyl group right here will be in part 2, and we will also refine their occupancies. So let's do that, and let's do it in 2 ways. So at first, let's do it totally by ourselves. Let's not allow Olex to write any restraints. So we can go to modeling and disorder tools. We can do split, but without any restraints, just split. I will show you why later. Okay, so let's do it. I can now click on the atoms we want to split. Split! And now we can try to fit them. So I think it's something like that, right? It kind of matches. If I now keep pressing shift, you can shift the molecule and escape, right? And great. So if I do now show P01, I can see now the part 0 and part 1. So here we have one disorder component. And if I now write show P02, I can see the second disorder component, right? So now let's go back, show P012. So we have one component, naming is as we set it to, and in the second disorder component, Olex automatically switch naming to 1A, 1A, 2A, 3A, blah, blah, blah. So let's try to write appropriate restraints now, because whenever you deal with disorder, it's always advised to put some restraints on the distances and displacement parameters. You can always delete them later if you don't want them. Okay, so what kind of restraints do we want? Let's have a look at our molecule. So we have 2 components. The main one, let's say, with a numbering C1, C2, C3, and the second one with numbering C1A, C2A, C3A, blah, blah, blah. So firstly, we want to make appropriate 1-2 distances similar to each other. So which distances do we want to make similar? So it depends. Firstly, of course, we want to make distance C1 to C2 similar to distance C1A, C2A, okay? But what about the benzene ring? We could, why not, put 6 different restraints. So the first restraint would be C2, C3, similar to C2A, C3A. Another restraint, C3, C4, similar to C3A, C4A. But actually, we know that in toluene, all of these bonds have very similar length, right? So we can treat the benzene ring as something with kind of 6-fold symmetry, right? So we can put similar distance restraints on all of these bonds from first component and make them also similar to the bonds in the second component. So let's do it right now. So at first, I want to take care of the bonds that are between the methyl group and the benzene ring. So these 2, I can do SADI 0.02. And now I want to take care of the benzene ring. So I'm going to click 6 bonds from the first component. 4, 5, 6. And also we want to make them all similar to the bonds from another component. And I think that's all of the bonds that I wanted to click. Yes. So we can do now SADI 0.02 again. So now let's take care of the 1-3 distances. So what distances do you want to make similar? So firstly, we would like to make distance from C1 to C3 similar to C1a, C3a. But also we know that the molecule is symmetrical, right? So we can also make distance C1 to C7 similar to C1, C3 and to C1a, C7a to C1a, C3a. Let's write it down. SADI 0.04, because we really want to treat the 1,3 distances with a bit weaker restraint. C1, C3, C1, C7, and we want them to be similar to C1a, C3a, C1a, C7a. Right? And now what about benzene ring? Again, we can assume that all of the 1,3 distances in the benzene ring are essentially very similar to each other. So we can put restraints on all of the 1,3 distances within that benzene ring and make them similar to that benzene ring. So let's do it. SADI 0.04, C2, C4, similar to C3, C5, similar to C4, C6, similar to C5, C7. And now, second component, or I think I also forgot about C7, C3. Yeah, C7. Also, I forgot about C6, C2. Okay, C6, C2, and C7. I don't have a great memory, so C7 to C3. And now, the second part, C2a, C4a, C3a, C5a, C4a, C6a, C5a, C7a, C6a, and C6a, we want it to be similar to C2a, C2a, C7a, similar to C3a. Yeah, so we've taken care of the 1,2 and 1,3 distances, so about the geometric restraints. And now we want to also put restraints on the displacement parameters. So we can put CMU. Let's leave it at the default value on all of them. We can also put regu on both components. And let's see how it's going to look like. Control R, let's refine. Okay, Control R again. So for now, we can see that the ratio of the two components is like 65 to 35. Between the two components, we can switch to anisotropic refinement, anis, Control R. And it doesn't look that bad, right? So if we would like, we can always change a little bit, make a little bit stronger the CMU restraints. So I usually, if I use CMU, I usually make it a bit stronger. So I put CMU 0.01, Control R. Our R factor went down. And well, now we can add hydrogen atoms, right? H add, Control R, Control R, and R factor went down even more, right? Control R, Control R. We can do more cycles, let's say 20 cycles. Takes some time, but now it's stabilized. We can also do the weighing scheme, and our R factor, especially WR2, should go down even more. Yeah, it's not optimized yet, the weighing thingy. Let's do more cycles. But yeah, that's basically the idea of dealing with disorder. I'll just wait until it's done. Yeah, I mean, we would probably need to do some more cycles, but it looks good. Okay, so now when we already took care of the disorder, it's always a good idea to look at the distances, whether the distances within the disordered parts make chemical sense. So I will just write show parts 0 and 1 to have a look at the first disorder component. So let's look at that bond. 1.49, I think that makes actual sense. That's the bond length that should be there. Here we have 1.4, 1.37. Well, it's all reasonable, right? And let's have a look at the second disorder component, show part 02. Here we have 1.5, and again, it's quite close to 1.49. 1.38, 1.38, 1.37, 1.36, yeah. So you can see that we still have some variation within these bonds. So if you would like to show part 0, 1, 2, make them even more similar to each other, I don't think it's necessary in this case. I mean, everyone knows that we have toluene here and that it's disordered. So we're not going to get perfect bond lengths, but we can also increase the strength of the restraints. So instead of default value 0.02, put, for example, 0.01, and here 0.02 instead of 0.04. But I mean, yeah, I'll just leave it as it is. So that was the first way of dealing with disorder. And I'm going to show you now the second way. And instead of using separate SADI restraints, we will use the same restraint.